We all know the old folklore. Someone's grandfather feels a deep ache in his bad knee, and sure enough, dark storm clouds roll in an hour later. For centuries, predicting the rain through physical aches has been treated as a quirky myth or an old wives' tale. In clinical reality, a drop in atmospheric pressure brings debilitating head and neck pain to thousands of people. Medical professionals have historically struggled to pinpoint exactly why a passing weather front triggers severe migraines and tension headaches, leaving patients without clear answers. Living with an invisible, unvalidated condition exacts a heavy psychological toll. Clinical surveys show these patients often experience high levels of pain catastrophizing, a mental state where a person fixates on their discomfort and feels entirely helpless against it. They also suffer from low self-efficacy, meaning they lose confidence in their own ability to function and manage their day-to-day lives. Between 2015 and 2018, Japanese researchers at Aichi Medical University finally found the physical evidence. By exposing subjects to controlled atmospheric changes, they proved that mammalian bodies contain an actual biological barometer. Weather pain is a measurable physical condition. To understand exactly how the weather takes a physical toll on the body, we are going to locate the specific pressure sensor hidden inside you, trace the biological chain reaction that causes the ache, and lay out 3 science-backed steps you can use to short-circuit it. Defining this invisible pain as a concrete biological reality is the essential first step. You cannot take back control from the weather until you know exactly how it is hacking your body. Dr. Jun Sato and his research team needed to identify the exact cells that react when the barometer drops. They created an animal research model where mice were exposed to a sudden 40 hectopascal drop in atmospheric pressure over 10 minutes, a reduction that closely simulates a severe storm rolling in. This animated cross-section of the human head reveals our hidden pressure sensor. Right here, explicitly labeled, is the inner ear's vestibular system, featuring the semicircular canals and a small structure called the otolith. Zooming into this system at the cellular level, we find specific mechanoreceptor proteins called TRPV4. These proteins act as microscopic physical triggers. When a typhoon or a heavy storm front pushes into your area, the TRPV4 proteins literally feel the drop in atmospheric pressure. Once activated, the inner ear fires a distress signal. That signal travels directly up to a specific region in the brainstem known as the superior vestibular nucleus, or SUVE. Prior to Dr. Sato's research, scientists believed this distinct pressure-sensing neural pathway existed only in birds to help them navigate flight. Mammals were not supposed to have this hardware. The human body maintains a constant, active monitor of atmospheric pressure, feeding environmental data directly into the brain's primary control centers. The superior vestibular nucleus serves as a primary gateway to the autonomic nervous system. When the SU is hyperstimulated by a sudden pressure drop, the brain processes this inner ear signal as a disruption to internal stability, reflexively shifting the body into a sympathetic fight-or-flight state. This autonomic shift disrupts the body's physical baseline, altering heart rates and awakening old injuries or exacerbating chronic pain sites. The clinical studies uncovered a striking physical symptom caused by this nervous system spike: severe blood flow disturbances localized entirely within the inner ear. We can see this disturbance clearly on this thermographic data overlay of a human head. The disrupted blood flow creates a stark physical temperature imbalance between the left and right ears. Patients experience a difference ranging anywhere from 0.6 to 2.5 degrees Celsius. That severe temperature difference persists while the storm is present, and entirely disappears the moment the atmospheric pressure returns to normal. A weather-related migraine is the direct consequence of localized blood flow failure and an overexcited nervous system reacting to a drop in the barometer. The pain is entirely physiological. The clinical study also yielded a vital discovery on the flip side of the equation. Environments with slightly higher atmospheric pressure do the exact opposite. They suppress sympathetic nervous activity and actively reduce pain scores. Higher pressure environments also significantly improve psychological symptoms. Patients recorded measurable drops in the anxiety and depression that typically accompany their chronic weather pain. Because we know low pressure restricts ear blood flow, the first actionable step is applying heat. Placing warm compresses directly around the ears manually dilates the blood vessels, restoring the temperature balance and short-circuiting the pain trigger. Step 2 focuses on the environment. You can utilize specialized pressure-regulating earplugs or rely on controlled air conditioning systems to artificially mimic the protective effects of high pressure on your vestibular system. Step 3 targets the nervous system itself. Engaging in deliberate parasympathetic activities, like deep-paced breathing, intentionally counteracts that biological fight-or-flight spike caused by the weather. The biological loop is a strict chain of events. Falling weather pressure triggers the inner ear, which overexcites the brain and the nervous system, resulting in physical pain. Applying warmth, regulating ear pressure, and practicing deep breathing breaks that exact chain. By understanding the precise anatomy of weather pain, you are no longer at the mercy of the forecast. You can transition from enduring unpredictable symptoms to actively managing your own biology.